Hi, everyone. We are live again, and it's Saturday. So I know you're excited to be with us. We want to make sure that you're ready to continue deep learning. So we want to thank you for joining us today with deep learning enthusiasts. And I realized that we went a little out of order last time because we had to push back a week, and then now we're breaking up chapters into smaller chunks so that they're more easily digestible for our viewers and for our presenters. So we want to make sure that everyone has a chance to really get the most out of this experience, learning the information. For those that are just joining us for the first time, we want to give you a little bit of background information on what we're doing. So this is an online discussion of the deep learning book from MIT. And we've decided for participants to gain the most out of this experience and understanding of the material, we have a volunteer each week present a section of the book. And so we were doing chapters at a time before, but we realized that it's getting more and more dense as time goes on. So now we're breaking it up into sections. And so we have Pankaj joining us again, covering the 6th chapter on deep feedforward networks. And so again, if you want to volunteer as a presenter, we do ask that you join on our Meetup page, and that's with AI and deep learning enthusiasts on Meetup in San Francisco, and also that you sign up on our presenter sign-up sheet. Now, I just restructured that a little bit, and you'll see if you are on the sheet that there are 2 sections, an online tab at the bottom and then an SF tab for our in-person version of this Meetup as well. And I've broken it up into 2 sections per chapter. Now, we might have to break it up a little bit more in the future if it continues to get more and more dense over time. But we're going to try at least 2 separate presentations per chapter for now and see how it goes. But anyway, let's go ahead and get started with the material. Pankaj, do you want to reintroduce yourself for the new people that are joining us this week?
Sure. My name is Pankaj Kumar, and I'm also been involved with the Meetup group for a while, and I've been a software engineer, and I'm also trying to learn deep learning. Yeah, let's get started.
Great, go ahead.
Okay, so last time we went through the half of the chapter, so I'll just give a brief tour of what we did last time. So we started with how neural nets are more expressive with this example, and then we went on to what cost functions are, and then a maximum likelihood as a cost function, and then we went on to output units and there's output units and the reasoning behind softmax and sigmoid output units, as well as hidden units. And then today we are going to start from the rest of the chapter, which starts with architecture of the neural network. And so the way most neural networks are organized is generally into groups called layers, and each layer is can be thought of as a function. And here, if you see H1 and H2, H1 is the first layer, and it takes a set of inputs X, and the parameters associated with it are W1 and B1, which is first a layer takes a set of inputs with X, which is a vector. And then it applies a linear function on it. W is a matrix, and B is another vector, and then G1 is typically a nonlinearity, a sigmoid or a tan H, and then the first layer, the output of the first layer, is fed into the second layer. So second layer is very similar to the first layer, if you see, but the inputs is the output of the first layer instead of the input itself. So here, so the book says that in the architecture of the network, height and width of the network is the most important factors. And it also says that as you increase the depth of the network, means you put H1, H2, more of them, it becomes harder to train, but the capacity of the network, the expressiveness of the network increases. So let's go to. So there is a very there's a very nice theoretical framework to understand this, which is called a universal approximator. So just to give some background, so we came like initially we used to use linear functions, but linear functions are not convex, so they can only approximate only linear functions or some functions. As if you come to the domain of nonlinear functions, then you would generally think that that nonlinear, like every class of nonlinear functions, for example, x square, x cube, you will kind of figure out from the problem what class it lies in, and then create a new function to a new function for it. But one second. So neural networks have this nice property, nice theoretical property that kind of says that you could approximate any. One sec, let me go back to present. Any nonlinear function with it, even though it becomes non-convex. You can the way it reads is that straightforward. That a feedforward network with a single hidden layer with any squashing activation function, such as logistic function or even ReLU, can approximate any Borel measurable function from one finite dimensional space to another with any desired non-zero amount of error, provided that network has enough hidden units. So it kind of says that a neural network can approximate any function. So Borel measurable function, like this, the book says it's outside the scope of the book, but it says that any continuous function on a closed and bounded subset of Rn, which is like n dimensional real vector. If there is a function defined on it which is continuous and closed and bounded, then it is said to be a Borel measurable function. And any Borel measurable function can be approximated using a feedforward network with a single hidden layer. So it kind of says that neural networks are enough for any nonlinear to capture any nonlinear function. And also it also says in a later derivation that even the derivatives of feedforward, so the derivatives of any Borel measurable function can also be captured by the derivatives of the feedforward network arbitrarily well. So these two kind of signify the power of a neural network. But even though it's a theoretical result, it's not very practical because of a few reasons. Because generally we are not given a function to approximate, but we are only given a set of training points to learn from. So it cannot just generate a set of test points arbitrarily and give you. So this theorem has some limitations. And also even though theoretically we know that a single layer can learn a nonlinear function arbitrarily well, the learning might fail itself because they cannot find the correct parameters or it may overfit. So it's not a silver bullet. And also it does not say how many hidden units will be required. And sometimes for some nonlinear functions, it can even be exponential. The number of hidden units required can even be exponential. So,
do you know, Pankaj, do you know of any examples in the real world that this would apply to, like where there would specifically be limitations with using that many hidden units? or hidden layers in the neural network?
In the real world, no, I don't know, but the book does cite that some problems there is like an exponential number of hidden units that are required for some problems. So even though theoretically it says that, oh, yeah, we could do it, but not practically it might not be feasible. But
Okay.
I don't know of a real function example offhand.
No, that's fine. Thank you.
Okay,
and also,
so,
we want to encourage our viewers that if you have any questions or want to add to the discussion, if there's something that you want to bring up, like that's the point of the chat windows. So please to chat with us and add to the conversation. We want to make this more of a group and a community collaborative experience. So we do appreciate our presenter, of course, for taking the time to explain as much to us as possible. So thanks again, Pankaj. You can continue.
Sure. So then this is a really nice picture representation. So now the author is coming, coming to the to explain why depth is required. Why do you need? So the universal approximation algorithm says a single layer is sufficient. But now he's saying, why do you require multiple? How does having more depth help a neural network? So here there is a very nice picture representation of how multiple layers could help. So for example, here, if we are using an absolute value as our hidden unit output function, then absolute value function, so if you remember, its shape is like it just puts negative to positive. So now if you see, if this plane, these are the given points, then you could draw a line in between, and so it could infer the patterns in this data. So it could find out, so for example, the first layer learns this line and then applies. And if you remember from high school algebra, then this line, the distance from this line is given by, so if the line equation is mx plus c, then mx plus c actually gives the mx plus c. If you put any arbitrary point, then it gives the perpendicular direction, perpendicular length from the line to that point, 2x. So this acts like a mirror function. So the mirror function, you can also think of it as like anything to the left of it at the same distance, same perpendicular distance from the line, will have the same will be mapped, will have the same output from that layer. So in a way, it's also saying that it's just folding this space along that line. So also, like the first hidden layer will fold it on one line, then the second hidden layer will fold it on another line, depending on the patterns it finds in the data. So if you see, the first pattern it finds is this that both sides have these sigma sine looking curve. So it folds along this. Then second is like it splits the sine in the middle. Then the third one, it splits another. So it creates different linear folds, and then those linear folds are easy. At the end of it, those linear folds are easy to classify into different types. So here it's like blue and red points. So it can finally, all blue points could be on one fold and all red points could be on one fold. And then you could just have a classifier like that. So this is a picture representation of how depth of the network helps. So let's go to the next. So this is from a paper from Montefiore, and he also states he also gives some theoretical results. So so he says that if there is a network with d inputs and it has a depth of L, and there are n units per hidden layer, then the number of linear regions like carved by those foldings is if you see it's exponential in D. So it's exponential in the number of in depth. So that signifies that only with a linear, if you have D layers, then it will be like exponential in D, the number of regions that you can carve out. So that gives you a lot of power. And also this is for absolute value output unit, and if you use max out as the output unit, then you can get the second equation, which is k to the power of L minus 1 plus D, which is also exponential in L. So it again gives you the exponential number of foldings if you in the depth of the network. So so he goes on to say that there is another way to look at how depth of a network helps. So here it's these are three. This is a graph of 3 different classifiers. One is a depth 3 convolutional network, and the other is a depth 3 fully connected network, and the third one is a 11 depth fully convolutional network. And if you see that the 11 depth convolutional network has a better test accuracy for the same number of parameters. So even if you have like a larger bigger hidden layer but less depth, then the test accuracy is not that much for both fully connected and for convolutional. So this for this particular problem, so it says that this kind of this suggests that using a deep model chooses a function from a class of functions which has sequentially dependent steps. So it first locates a set of objects, then derives something on top of it, and then derives something on top of those results. So because that function it can prefer, it can have a better test accuracy. Also, then the book also goes towards other in architecture. What are the other considerations? So this is not the only, like a feed-forward network is not the only architecture that you can have. There are other architectures, other ways of connecting layers to each other. One example is a convolutional neural net, and then another example is a recursive or recurrent neural net, and then there is also one thing you could do is, like, so far in we connect all units in one layer to all units in the next layer. So you could choose which units to connect and which units to not connect, or you could also choose some connections that go from one layer to, like, not just the next layer but to subsequent layers. So what this helps in is, like, the gradients can flow easily to layers, previous layers. So those are other considerations when deciding the architecture of a neural network. Then the book comes to back propagation. So I just made this graph just to give an introduction to the rest of the section, and this one is for example, here, if you see, forward pass is basically if you get these 3 first. Let me draw this so this will become better. So so these oh, sorry. So these three are the first layer, and then and then they are connected to. So they give some inputs to the next layer, and then those inputs are go through a linear unit and then a sigmoid unit, and they compute x1, x2, x3, and x4. And then at the last layer, there is another, for example, a linear unit plus and another softmax function to compute this y hat. So if you see this formula, and then we compute the cost. So we know the real y. So when we are training, we know the real y, and we know the initial input. And then at the end of it, we can impose a cost function j theta y hat y. So y is the real y, and y hat is what we computed from the neural network. And then so this is the forward pass in a neural network. And then the backward pass actually computes the gradients for all parameters. So for example, the parameters for the gradient with respect to theta 1 for the cost function, with the gradient with respect to theta 2 for the cost function, theta 3. And this theta 1, theta 2, theta 3 repeats in every layer. So if you see, this is just on the last layer. So these parameters are only the parameters on the last layer. The same type of parameters are also in the previous layer and the layer before it. So the gradient, the way the gradient is calculated for all the layers, we calculate it for the first layer, and then we use that to calculate it for the layer before and for the layer before, and that is what backward pass is. And once we have calculated the gradients, we can do this thing called stochastic gradient descent, or another form of descent, to get to an optimum value of the parameters for this network. So that is the optimization part of it. So the book, I just made some things for an introduction. The book goes through details of how it's done. So now we'll go through that. So just to give an introduction, this is what the book calls a computational graph. So each node is some value, and it gets calculated with some operation from some values before. So here the a is just x multiplied by y is z, and then if you see b is actually a linear unit. So it's x multiplied by w weights and a dot product, and then you add to it a b to get x and w dot product to u1, and u1 and b add to u2, and u2 there is a sigmoid to a y bar. So that is a sigmoid unit, hidden unit. And C is same thing for a ReLU, and D just says that there could be multiple, in a computational unit, there can be multiple outputs. So for example, here y bar is one output, and then u3 is another output. So y bar is xw, and u3 is kind of modeled as a regularization parameter that we can think of. So if, for example, we are computing a cost function on y bar, it's not the full thing, but u3 can sometimes be seen as a regularization parameter. As w increases, u3 increases, so the cost increases. So from in the figure D. So that's okay. So this is how they represent computational graphs in the book, and this will come in handy in the later slides. Also, the chain rule. So simple chain rule is like, if you have a recursive functions, y is equal to gx, and then there is a z function which is fy. Then, and let's suppose these are all continuous and differentiable all over the place. Then dz by dx can be written as dz by dy multiplied by dy by dx. This is a chain rule, and this is what gets used when we propagate. So for example, when here we calculate the derivative of this cost function with respect to theta 1, theta 2, theta 3, then this chain rule comes in very handy to compute the gradients with respect to other parameters in the network. So we'll come to that soon. And then the chain rule also, you can also see the chain rule with respect to vector notation. So here, if you have two vectors, z, if the same thing is acting on so if z is a scalar, but x and y are vectors, then you can write the same thing as this is the differentiation of z with respect to x. X is a vector, z is a scalar. On the left-hand side can be written as the Jacobian of y with respect to x. So y is a vector and x is a vector. So it will have a Jacobian. A Jacobian is like each ij is the differentiation of the ith element of y with the jth element of x. So it's a matrix. So you can think of it as a matrix multiplied by the differentiation of z with respect to each element of y. So this is in the matrix notation, and this gets used pretty extensively. And also the book says that the same thing that we are doing with respect to vectors can also be extended with respect to tensors. So tensors are multidimensional arrays. So you can treat them as regular vectors, and then the same rules that apply to vectors can be applied to tensors as well. And
we had a quick comment in the chat. Abdullah is asking, do you mean composite function?
Yeah. Z is f of g of x. There is a composition going on here. Mm-hmm. And if you see from this formulation, this is a composite function. So if you just take h1 g, if you a neural net is a composite function. So if you take g2 and then h1 is another function. So this is h2 of h1. It can be also written in the form of h2 of h1 x. So a two-layered neural network can be kind of written in this form. So this is a composite function. So that's why the chain rule becomes very useful, because this is a
great. Thank you.
Function. So okay. So then the book goes on to so then they're actually giving what a forward pass and a backward pass is. So here I'll just go through. Here, if we have a network of depth L, and we require Wi, and they all have weights and biases, and there is an input to this. So Wi is, so let me see, which is layer 0. I'm just trying to see. Okay, so layer 1 is, so in this figure, you can see this is this. Let's suppose these are inputs. So these are 3 inputs, x's, and then the W signifies all these weights, all these connections, and then there is W and B. So W and B compute one value, which is A. So here, if you see, W and B of each layer computes an A, which is just a linear transform, and then the H is also a nonlinearity applied to the sigmoid or tan H applied to that AA. And then then there is a y hat at the end, which computes the final softmax, for example, even here. And then the loss, the j here, also has a regularization term. So it's actually penalizing penalizing very big weights. So this theta you can think of it as something that contains all these weights and biases, and theta is a set of all weights and biases. And then this delta is a parameter, and then this is penalizing all of them, so they don't have like a very big value, so we can actually learn better. And so this one just goes through each layer and then computes the linear output and then the sigmoid or tanh output for each layer. So this is the forward pass. And then in the backward pass, we go from the last layer to the first layer. And G is the derivative that is coming from the next layer into this particular layer. Goes from L to 1, which is all the layers, and then G is the derivative that is coming into that particular K layer, and then we compute this. First we compute the derivative with respect. We compute the next. Wait a second. Convert the green. Yeah. So first we compute the gradient of that layer to a gradient before nonlinearity. So first we differentiate with respect to just the nonlinearity. So because we are applying the chain rule, we are going one step behind, and then this G changes. And then if you see, so for example, if the nonlinearity is a sigmoid, then then we are taking the differentiating with respect to sigmoid and then coming back. So, I don't think I'm explaining it correctly. So here, for example, the G for this layer, for this last layer, the G is the derivative with respect to the output of this layer for the cost. So it's D of cost divided by the output of this layer. So in the first step, we are going just behind and this layer has two operations. One is a linear operation, and then the second is a nonlinearity, right? Tanh. So first we are going behind the tanh. So first, using the chain rule, we are just trying to get the derivative with respect to the input of tanh instead of the output of tanh by multiplying by doing some mathematics. So we can do in this first line, and then when we have that, then we can get the derivatives with respect to the theta 1, theta 2, theta 3, theta 4. Once we have, because then the input is just a linear combination with respect to theta 1, theta 2, theta 3, theta 4. So we can get that derivative. So that's what is happening in this line, which is the W and B, the derivative of cost with respect to B and W. And also see that there is a term here, and there is a second term here. This is the derivative with respect to the regularization term. So the cost function also has a regularization term, but it's very straightforward. Like the BK, for example, just becomes a BK square in the regularization term. So it can be easily differentiated with respect to BK. When we differentiate with respect to another weight, then it does not come to play. So we can just differentiate with respect. So this is the differentiation with respect to each weight and each bias, and then we again change the G so that the next layer can use it. So then we change the G and repeat this whole thing for the next layer. So this is the backward pass of computing all gradients with respect to all parameters in all the layers. But so this is the theoretical way of doing it. The way generally like a software package would do it is differently. So the way software packages do it is, for example, if you have like a simple W and then you apply a F, which gets to an X, and then you apply another F. So they make when you give it a neural net to make, then they make it into a computational graph. And then the way they will compute is at every layer they will. So if, for example, if all of these are F, then they will compute it. They call it symbol to symbol approach, and both Theano and TensorFlow use it. And they will compute a different graph, which will actually compute all the gradients. So they will compute this because from this graph, they will compute F dash with respect to Y, F dash with respect to F. For each layer, then this second one is, if you see, dz by dx, and then this dz by dw. So all of them, they can wait, dz by dw. Yeah, so dz by dx multiplied by dx by dw is dz by dw. So they will compute this dz by dw using this second computation graph. And
so we have a quick comment from Abdullah. It says, we take the derivative for each node separately. Could you elaborate on that?
For each node separately. I don't know the exact implementation of Theano and TensorFlow, but from a conceptual way, I think we can do it this way. So you could take it. If your computation graph that you give that you have supplied to Theano and TensorFlow looks something like this, then each you can easily do one-step derivative, then two-step derivative, and a three-step derivative. So a derivative of z with respect, what we are looking to find is a derivative of z with respect to derivative of w. And you can first find one layer, then you can combine two of them to find a two-step, and then you can combine two of them to find a three-step derivative.
Yeah.
Does that answer the question? Cool. Okay. And so the book also mentions another method where instead of doing, so some approaches do not actually give out the derivative with respect to each node and each parameter, but only with respect to the input only with respect to the weights. And so Café and Torch, they do not create this graph, but only give you the derivative with respect to the inputs and with respect to the weights. So so that's how. So but they're similar, but just that Theano and TensorFlow give you a little bit more control, it seems.
We have another comment from the audience. Is both Theano and TensorFlow, there's auto differentiation of being implemented already.
Yeah. This is how they do it. This is auto differentiation.
Yes.
Yeah. So then this is nice. They actually how. So then they go on to the implementation of how to compute these general backpropagation. So let me explain. The book explains it, but I didn't put it. So there are a few things. So if you have a layer, then get operation is actually doing. So if you have a layer, it has some inputs and some outputs, and the inputs are connected. If you have a node, I'm sorry, not a layer, but a node in a computation graph. So for example, this is a computation graph. Then every node has an input an output. The input comes from some other nodes, the output goes to some other nodes, and there is an operation that happens in this node. So in that case, here you can compute the whole back propagation in that computation graph using this algorithm that is outlined in the book called the general back propagation. And the way they do it is basically they go to each node and they initialize a gradient table Z. So for each node is 1, and then they tensors. So tensors to their gradients. So for each parameter, they are putting a grad table to 1, a gradient. Wait 1 second. Let me read again. Require T the target of T the target set whose gradients must be computed. G the computed. Is Z the variable to beat? Okay. Okay, so what is V? I think I left out something that is there in the book. I don't see what V is. So basically, the idea here is that that in this grad table we have the gradient of each node as we compute them. So this is like we are computing a gradient and we are putting it in the grad table. And now for if we are given a node to if we are given that we need to compute the gradient for that node for parameters in that node, then what we do is we go to each layer. So for example, here if we are given to differentiate with respect to, for example, this W2 or W2, for example, then what it will do is it will recursively call the differentiation of U5. So it will make sure that U5's gradient is already computed by recursively calling each build grad on each of its consumers. So U5 is a consumer of W2. So so it will actually compute the gradient with respect to U5. And then after it knows that everything has been computed, all its downstream elements have been computed, the gradient for all its downstream elements have been computed, then it actually it also gets the GI, which is a gradient with respect to that output. So in this figure, if you see, well, W1 has two. This is a good case. W2 has two outputs, U2 and U5. So first it will compute the gradient U2, and then it will back propagate from U2. It will get the differentiation with respect for W2 with respect to U2, and then it will also call the differentiation with respect to U5 for the cost function, and then it will back propagate from there. So it will have two GIs. So if you see here, it will the get consumers will have two nodes for W2, and then it will get two gradients, and it will add those two gradients to get the gradient for that particular W2. So this is how the general back propagation for a computational graph works. And this is
actually there were just a few more comments in the we wanted to make sure that we're keeping up with that as well. So sure. It says back to here on TensorFlow and Theano, it says in TensorFlow and Theano, the differentiations are done symbolically. Mm-hmm. And you said he was his comment on, I think that's what you meant by auto differentiation. And then they did post a link as well for reference, and I'm going to go ahead and post that within the Excel spreadsheet.
I'm not
so if you guys
seeing
want,
it. 1 second. Can you send me?
Yep. So in the chat
okay.
window on the right hand side, it's in there. Yep. And so we have that posted as well for you guys. And then let's see, we've got Abdullah. He says, we know these operations are very intensive in terms of computing power. Which frameworks that you've mentioned do it faster? Do you know, Pankaj, which ones might do it a little bit faster?
I don't know, but there are some comments in the slides itself. So I think I have it written somewhere, but maybe it was no. So there are a lot of optimizations mentioned, and it seems like if we go forward, and some of them are implemented in Theano, and some of them are implemented. So I don't have practical experience, but from the book itself, it seems like Theano and TensorFlow have more of these optimizations built in. So maybe they are faster. So that's what I got. So for example, they talk about this particular optimization. So I was going to come to this later, but I'll just mention that this optimization, which is, so a softmax function, for example, can be easily differentiated. It need not have like the whole computational graph, but it can be easily differentiated as the output vector minus the real the training set output. And the Theano has some improvements like these built in, but others probably don't. That's what the book kind of hinted. So I would guess Theano and TensorFlow seem to be more optimized.
Thank you.
And okay, so I can go through. So this is. I'll just go through this. This is a nice example. This is a full neural net computation graph. So if you see, if you forget the left portion, these W1, U3 sum, this is just the. So if you make a cut, let me do that. Line. If you make a cut here, and another line here, then everything to the left is the cost from the neural net, and everything from the right is the cost from the regularization terms. So here, if you see you are given x, and then there is a linear function, and then there is a ReLU. So there is a hidden activations, and then there is another linear function and some another linear functions. This looks like some just some matrix multiplication, and then there is a cross entropy cost with respect to the actual y that the training set gives, and then this cross entropy cost is JMLE, and then this gets added to the regularization cost. And this regularization cost is just a square of the weights, and then you sum all the squares, and then you add them together and multiply it with a lambda. So this is the regularization cost. And if you run this particular algorithm, general backpropagation, through this computational graph, then you will get all the gradients. So that's how the general backpropagation works. But the book kind of mentions there that there are other problems with this as well, like the tensors, the way you put it in the memory could use too much memory, or sometimes for the non-linearities you could find undefined gradients, and sometimes you have like different data types. So how do you put them together and differentiate back to them? And sometimes there are more than one tensors as outputs, so that causes some that causes problems. I forget exactly how, but
a few more comments.
Yeah.
Faison says, one more thing that helps speed up the process is parallel computation. So most of these optimized Llano can work with GPUs which run these operations parallelly, which minimizes the time taken for completing the operations.
Yeah, for sure. I'm guessing all of them, like TensorFlow, Theano, Caffe, all of them run on GPUs. Maybe one does better than the other, but probably all of them do. Okay.
Technically, like you can implement.
I'm hearing some static, Laura.
So ask, well, can you hear me? Yeah.
Yeah, now I can hear.
Yes. So I was all these different libraries. You can also write to use GPUs.
Yeah.
Efficient if you use GPUs.
Yeah, all these have support for GPUs, so that makes them faster, of course. Yeah, this chapter somehow does not touch upon GPUs at all for some reason. So it goes on.
Well, maybe we'll get to it later on.
Possibly. Okay. Cool. So we are.
That's okay. We can continue.
Okay. Cool. Thanks. Can everyone hear? Because I'm having trouble hearing.
I can hear you guys just fine, or I can hear you.
Okay. Cool. Okay. So then, so this backpropagation is one of the techniques in a class of techniques. They call them a reverse mode accumulation. So it's like. So also, if you see that they're computing the last layer, then using that to compute the second last layer, and then the third last layer. But it can be, it may be that if you do these computations in a different order. So for example, if you do the third last layer and fourth last layer together, and the second last layer and the last layer together, and then you combine them, then it might require less computation. But finding these sub-expressions and finding which is the least expensive is a harder problem. It's NP hard. Like I was mentioning, some of the optimizations, for example, the softmax function can be easily expressed by y hat minus y, but they don't really show up in a real implementation because they don't know how to optimize like just by seeing that this is a softmax. But Theano actually seems to know when you use a softmax, then it actually does not do the whole computation graph, but only does a y hat minus y. Just takes a difference between the output and the real vector, and that's the derivative. So also there is a thing that the author claims is that when the forward computation graph has a single output and each partial derivative can be computed in constant amount of computation, then the backward pass can be done in the same order of computations as the forward pass, and also it can be optimized. So it's computationally, if you think about it, the forward pass, the double of the forward pass is all the computation you need to do a backward pass. So it's not impractical to do it, because the forward pass, if you see, is very simple. Just some weights, some linear functions, and then some non-linear non-linearities, and then you get to a cost function. And if you and the backward passes, if they have the same number of computations, then it becomes then it's feasible. Okay, so this is the So there's another one. So the book talks about, so reverse mode accumulation is one way to do it. So forward mode accumulation is also a set of techniques in which instead of going from last step to first step, you go from first step to last step in doing this. And one of the techniques then cited by the book is like, if you know, like if you have 4 matrices, then the way you multiply those matrices depends. Like if you multiply the first 2 together and then the third one and then the last one, versus if you multiply the last 2 together and then the third last one and the fourth last one, the number of computations can differ. So this also applies a similar kind of method to figure out the least number of computations. So that is forward mode accumulation. The book doesn't really go into a lot of detail on it. Just says that it's analogous to matrix multiplication and you can optimize how many actual multiplications you do. And then the last slide. This is the last slide, and this is so this goes on. The book goes on to higher order derivatives. So higher order derivatives could be very useful. If you have the higher order derivatives, you could know where the maximum change in gradient is, and you can go in that direction. But the problem with finding higher order derivatives is the computational overhead. So if you have a function that takes, like the cost function, it takes a vector and produces like a single cost value. But if you take a second degree, Jacobian is a first degree. So if you have a function Rn to Rn, then the Jacobian is n cross n. But the Hessian is n cross n, even if Hessian is the second order version of Jacobian, which is in which each term is a so for example the first so if you have a Rn to R, then the first term is d square y1 by d square x1, and then the second one is then 2 is d square y1 d square y by d square x2, and similarly. So the Hessian is of the shape n cross n, even for a single or for a function that outputs a scalar. So it becomes harder to compute, and that's why it's not generally used during optimization. But the book also says that there are some methods called Krylov methods, and these methods are these methods are iterative techniques for approximating certain things like eigenvectors and eigenvalues, and for a matrix, and they can be used. And so here it actually gives an example. So if you take the Hessian and multiply it with a vector, then by this method you can also compute it by using so fx is the actual function for which h is the Hessian, for example. So Hessian is the second degree matrix, second degree differentiation matrix, and then this one becomes a sigma x fx. I'm calling it sigma x. I'm not sure what it's actually called. Sigma x fx, and this is the differentiation of fx with respect to with respect to x, a first degree differentiation, and then you multiply it by v, and then you multiply it again by the same quantity. So this is an approximation of hv. So for any arbitrary vector. So this can sometimes be used in deep learning, but directly computing the Hessian is not generally used. So then the book goes into some historical concepts which I did not really put in the slides. So, but that's all the chapter for deep neural net is.
Wonderful. Thank you so much, Pankaj. That was like super in depth, and we really appreciate all of your time and also taking the time to build out some separate examples for us that weren't necessarily covered in the book to make sure people had all the background information going into this section. So thank you again very much. And I want to remind people, so Pankaj has his own, he's a founder of his own company. It's called Data Cabinet. What's the website for that?
We are still building it. We changed a lot, but it's going to be datacabinet.info. There is something we built before, so it's still part there, but we're building a new one.
Awesome. But yeah, they are actually applying for Y Combinator, so let's wish them luck. Hopefully they can get in, and then if not even, like, it would be great to see their startup thrive. So of course we want to make this a community situation, so let's all support our awesome presenters and volunteers as well. And then also for our next chapter, we're going into chapter 7, regularization for deep learning. What I did was I broke up the chapter into 2 sections. So the first half, which will stop at it stops at early stopping, which is kind of funny, on page 252. And then the second part of chapter 7 will be starting at parameter typing and sharing on page 253. We do actually need a volunteer to take on chapter 7. If anyone is willing to volunteer, you can just sign up on the presenter sign-up sheet, which is located both on the Meetup page and then also on the YouTube channel under the link. So we would appreciate if someone would be able to take the time to do that. And then for the presentation itself, like we've said before, it can be as short as 10 minutes, as long as an hour. The longest we've had is 2 hours so far. We don't want to go much past that just because we want to respect everyone's time and energy for this that they put into doing the presentation for us. So thank you very much for that. And then for people that are just joining us, we also have in-person sessions here in San Francisco. We're covering this book as well in person, and our next one will be this Monday, and actually Pankaj is going to be doing chapter 6 for us there for these deep feedforward networks. And then we also cover different lecture series, which happens on Thursdays. So we're currently going through deep reinforcement learning lecture series that's put out by Berkeley, and previously we've covered Stanford CS231N on computer vision. So just to give you guys some background information on how that works as well. As a group, we get together, we review each video lecture, and throughout the time, we pause the video and just have a discussion or ask questions, make sure people really understand what's going on and what on the topics that are being covered as well. And we also try to get together to do the assignments and the homework as a group, just to really encourage people's learning and get them going in deep learning and AI. So we want to thank everyone for joining us, and thank you again, Pankaj.
Thanks, Laura. Thanks a lot.
Yeah, of course. So yep, bye guys. We'll see you later.
Thanks.